Intensity-dependent normalization methods differ in that they correct the intensities depending upon their level. This is accomplished by applying a nonlinear transformation to the data. Therefore, intensity-dependent normalization changes the shape of the distribution. In 1983, Bland and Altman examined the medical literature for commonly reported statistical methods for comparing two methods of measurement and found that correlation was most often used to assess agreement. For example, correlation was used to answer the question, do the two methods of measurement give answers that are comparable? They demonstrated that correlation is not a useful measure of agreement, but is rather a measure of association. In addition, they demonstrated that it is very easy to identify linear patterns from a scatter plot, even when the linear pattern is not particularly strong. Therefore, they proposed the use of a 45-degree rotation of the scatter plot, now termed Bland-Altman plot. A Bland-Altman plot plots the average of the two measurements on the x-axis and the difference between the two measurements on the y-axis. This plot enables one to more readily assess the magnitude of disagreement and whether there is any dependency upon level of measurement. In the microarray literature, these are usually log base 2 transform plots, which are referred to as MA plots, or M versus A plots. For a single custom spotted array, creating an M versus A plot is helpful to achieve normalization. The MA plot consists of plotting for each spot on an array, M, which is the log base 2 ratio of signal intensities, versus A, which is the log base 2 average. The plot typically demonstrates the need for intensity-dependent normalization, that is, the need to apply a different correction depending upon the level of gene expression. This is an example of an MA plot. Although the two samples can be different for different genes, the majority of genes should have roughly similar expression levels across both samples. Therefore, on average, the difference M should be 0, and the difference should not depend on the average expression values. Here the trend is for the difference to fall below the y equals 0 line, and therefore intensity-dependent normalization would likely help. When performing intensity-dependent normalization, the correction is still given by the same equation. However, the correction C is no longer a constant. Instead, C is some smooth function fitted over all spots or probes. Most often, robust locally weighted regression of intensity log ratios M on the average log intensity A is performed over the entire array, a process we call global Lowess. The seminal paper on this topic used a span of 40%. Other methods such as smoothing splines or exponential fits may also work well for intensity-dependent normalization. So let's first look at how Lowess regression works. Locally weighted polynomial regression, or Lowess, is an approach for analyzing nonlinear data, which is attractive because it relies on the data to specify the form of the model. A model is fit locally so that at any point the fitted value depends only on the observations at that point and some specified neighboring points. Because such a fit produces an estimate of the response that is less variable than to the original observed data, the result is called a smooth, and the procedures for producing such fits are called scatterplot smoothers. To avoid overfitting, Lowess fits a 1-degree polynomial, while Lowess fits a 2-degree polynomial. In locally weighted regression smoothing, we build the smooth function pointwise as follows. First, take a point, say x naught. Find the k nearest neighbors of x naught, which constitute a neighborhood, n of x sub naught. The number of neighbors, k, is specified as a percentage of the total number of points. This percentage is called the span. Next, calculate the largest distance between x naught and all other points in the neighborhood and call the maximum distance delta of x naught. Next, assign weights to each point in the neighborhood using a tribe cube weight function, which is given by this expression. Then calculate the weighted least squares fit on y given the neighborhood n of x naught. That is, only calculate the regression equation for the points in the neighborhood and be sure to apply the weights. Then take the fitted value at x naught and save that value. We then repeat these steps for each value in x. Let's look at a specific implementation of Lowess regression. First, for the U.S. arrests data frame in R, here is a scatter plot of murder by assaults. In step 1, we identify a point. Note the point here. To find this point's nearest neighbors, we calculate the distance from that point to all other points in the data set. Supposing our span is 50%, given that there are 50 observations in this data set, we select the 25 closest observations to this point as the neighborhood. Then in step 2, we identify the largest distance between x naught and all other points in the neighborhood. That gives us our delta of x naught. And in step 3, we assign weights to each point in the neighborhood. Note that the weights will be the largest for points near x naught and smallest for points in the neighborhood that are farthest from x naught. Then fit the weighted least squares regression model predicting y using the observations only in the neighborhood n of x naught. Take the fitted value and save this prediction for x naught. In this case, the fitted value is 8.707. Let's now repeat this procedure for a different point. Notice we have selected a new x naught. Now we have identified its neighbors using our span of 50%. Then in step 2, we identify the largest distance between x naught and all other points in the neighborhood. This again is delta of x naught. And in step 3, we assign weights to each point in the neighborhood. Then fit the weighted least squares model predicting y using the observations only in the neighborhood n of x naught. Take the fitted value and save this prediction for this new x naught. In this case, the fitted value is 5.139. This, of course, would be tedious to do for all data points because we eventually want to connect a line between all of these individual predictions. R includes a function, Lowess, that can be used to fit Lowess regression. This example can be executed in R as US arrest is a resident data frame that can be loaded into your R workspace using the data function. You may want to examine the help for the Lowess function. We can fit a Lowess model using the syntax where murder is modeled by assault, and these vectors are in the US arrest data frame. We specify that the span is 0.5, which indicates we want to use 50% of the data for fitting our local models. We also specify that the degree of the polynomial is 1, which fits a linear model. When the degree is 2, that fits a 2-degree polynomial, which is the default. Then we can plot our data and overlay the fitted Lowess curve. Note these 2 points on the curve. They were obtained in our 2 specific pointwise Lowess models and correspond to the first and second example, respectively. To summarize, the steps for intensity-dependent normalization for custom-spotted arrays are: first, for array K, fit a Lowess regression to the MA plot. Second, obtain the fitted values m hat sub jk. Third, adjust the probe intensities using this equation. This will normalize the log difference. To normalize the data on the original scale, this is equivalent to applying this adjustment. Alternatively, one may be interested in adjusting for important experimental artifacts such as location, that is, subgrid on the array, or print tip. Recall that custom spotted microarrays are manufactured by spotting the probe cDNA in circles by a series of print tips. However, there are often variations in the amount of deposited probe DNA among spots on the same array. This is called between print tip variability. And there may be also variability in the amount of probe DNA printed between spots on different arrays. That would be within print variability, or differences in the size and shape of deposited target. Therefore, justification for adjusting the intensities by print tip is due to potential variability in length of print tips, diameter of tips which deposit the probes, deformation of the print tips as a result of continued use, etc. Normalization by print tips is usually accomplished by using robust locally weighted regression to model the intensity log ratios M on the predictor variables. Rather than apply this global Lowess normalization method, within print tip group Lowess may be preferred, whereby robust locally weighted regression of intensity log ratios M on the average log intensity A within print tip groups is fit. The adjustment C sub jk is now the fitted value from the Lowess regression for the ith print tip, the jth spot on that print tip for the kth array. In the active learning lab associated with this module, you will practice reading in raw custom spotted array data, constructing MA plots, and applying normalization methods.